So, hello everyone, welcome back. Now, let us discuss problem number 5.10 of Griffiths electrodynamics, chapter number 5, magnetostatics. So, this says the A part says find the force on the square loop placed as shown in this figure, A part, and near an infinite state wire. This is an infinite state wire. Both the loop and the wire carry current I, it is given. So first of all, let us mark the coordinate system. Suppose this is X, this is Y, and outside I am taking Z. This is the uh, model for outside, and if the magnetic field or the coordinate system we can say is this is inside uh, minus Z cap, this is plus Z cap, this is minus Z cap. These are the coordinates. This is the coordinate system. So we are given that we have a square loop of side A, and we have an infinite wire which is at s distance from the square loop, and current is given like this. You can say clockwise and like this in the wire. So we need to find the force on the square loop. So force on the square loop due to infinite wire. All right, so the formula for this is current for the square loop, or you can say it as some small force, df force, but I am considering it as capital F. uh, Current of square loop into the length of square loop. If the force is small, then length will also be so small, but we are considering uh, force as big, so length can be considered as big. So current of square loop, length of square loop multiplied by magnetic field of infinite wire. So this is the formula for force acting on a square loop uh, due to an infinite wire. It is also given as df is equal to I dl cross b, where dl is in the direction of current obviously, and b has its own direction. We'll calculate, we'll see it now. So now what happens is we need to calculate first of all the magnetic field for infinitely long wire, because we need that here. So magnetic field for infinitely long wire, we very well know it is given by mu naught I upon 2 pi into the distance from the point we are calculating. So the distance is s here. So for the point, for the side, this is given by uh, the magnetic field is given by mu naught I upon 2 pi s. Now we'll be putting, so we need to calculate force on all the four sides and then evaluate it eventually, because the whole the four side will collaborate and give the force. So first of all, let us calculate on this side: 1, 2, 3, and 4. So force for 1, it is given by current I, and the the length which is of length for the this side is a, and it is in I cap direction cross what is b. B is mu naught I upon 2 pi s, and the direction of b. So the magnetic field we need to calculate is for this infinitely long wire. So we'll put the thumb in the direction of current and curl our fingers. So as soon as you curl the finger, you'll see that the magnetic field is in the z cap direction. So, or you can say that k cap direction. All right. So we got that force as I square a mu naught 2 pi s, and the direction of force is minus I cross k is minus j. So yes. Now for side number 2, it is also given as I a, the direction is in the j cap direction, because the current the dl direction is the current direction actually. But a small error here is the dl direction is negative, sorry. So one negative also appear because the dl is minus x cap here, because you can see it is pointing towards minus x cap. So it will become as mu naught I square a upon 2 pi s j cap. So now force due to side number 2 I, the distance, oh sorry, the length and the direction is in the j cap. You can see upward. The dl, I again repeat, the direction of length is same as the direction of current. So a j j cap cross mu naught I upon 2 pi s into the direction of this. So we get as mu naught I square 2 pi s into j cross k is I cap. Now f3 is I. Here the length is also this, and the direction is here I cap. Why I cap? Because it is in the x, positive x direction. So mu naught I upon 2 pi, but now the main thing here is that the distance has changed now. It is s plus a now, because you can see that this point is a s plus a times s plus a times away from this. All right, and the direction is the magnetic field direction is same. So we get mu naught I upon 2 pi s plus a, and in the direction of minus j cap. So now for f4 it is I a, the direction is in the minus j. I hope it is clear now why minus j. So into cross mu naught I upon 2 pi a 2 pi s, sorry, and k cap direction. So you get mu naught. Here I thought, I think a is left. Mu naught I square a upon 2 pi s, but in the minus I cap direction. So from the figure you can see that this is 1, this is 2, 3 and 4. So 2 and 4 are cancelled, so we can cancel them. So net force F net is given by F1 plus F3, and which is actually F1 is mu naught I square a upon 2 pi s j cap direction plus mu naught I square a upon 2 pi, sorry, I square and a will also appear, 2 pi s plus a in the minus j cap direction. So this is the net force acting on the uh, net force acting on the square loop, sorry, net force acting on the square loop of side A, and which is due to the infinite you can say length, infinite length of wire. So that's the part number A. Now let's go to part number B, which is a triangular figure. This part is interesting. So we'll be going to the part number B, and we have a, let me draw the triangular figure again. Yeah, so that figure is somewhat like this. Sorry, this is an equilateral triangle, pardon me. I think I should draw it like this. Yeah, yeah, that's better. That's even looking good. So this is a equilateral triangle, and we have an infinite wire here, and it is a distance, I guess, s, and we have a equilateral triangle of side E. So we need to calculate force on this triangle due to infinite wire. I guess this is the question. Let me read that again. Find the force on the triangular loop. Yes, and current is clockwise and direction is this. So we have current like these, I current like this, and I current like this. The question is just similar. We need to do calculation only. That's important. So first of all, let us define here df. Why df? Because the figure, we can see that figure is not as symmetric as we have in that question. So we will write it as I dl cross b. All right. because we need to consider small strip, I guess, in this question. If we are not to consider, then this is the important formula. We need to remember it like this only. So you'll remember like this only. And magnetic field will also be same here. Mu naught I upon 2 pi, the distance. You can say that, and you will write d only. Distance will change it. Let d be the variable here. Variable. We'll change it later on if required. So first of all, uh, we'll we very well know that for force due to this side, let us mention 1, 2, 3. Force due to 1 is similar mu naught I upon 2 pi s, and it is in the direction uh, mu naught I square as, and it is in the direction j cap. It was already calculated. So now we'll have to calculate force due to second one. So force due to second one, df2. So we'll use the formula. So I of triangle obviously, and the length dl is, it can be written as dx I cap dy j cap dz k cap and cross b, and obviously b for the infinite loop or infinite wire, b for the wire. All right. So we'll again uh, put things in the formula. df2, it is equal to mu naught, we'll be putting the value of b mu naught I square 2 pi. Interesting thing is, the magnetic field is in the direction of is in the is magnetic field is in the direction of k cap, and this distance, because as this distance is increasing from this wire, so this is also increasing, this is again increasing, this is again increasing, means if I am increasing x, then y is also increasing. All right. So it means we have a variable here. So we'll be using a variable because y is changing, as we are changing x, y is also changing. So we can see that magnetic field b for wire is given as mu naught I upon 2 pi y, and is in the direction of k cap. Why? Because we need to uh, take limits, and for limit we either you use x, but we have an infinite wire, so x is not defined and we need to calculate x. So I'll be using y just to define my limits according to this point and this. It will help me later, you'll see. If I take x, then finding limits will be slightly more difficult to me. So mu naught I, this I and one I from here, I square 2 pi y, and now it is in the k cap direction. So for k cap direction, we need to be very careful about how the cross product will work. So dx I cap plus dy j cap plus dz k cap cross k cap. This k cap is for the from the magnetic field. So we get mu naught I square 2 pi y, uh, I cross k dx minus j cap plus dy I cap, and it will be 0. So we can see that the force is somewhat is in the form of these coordinates. So now we very well know that we have to use the straight line formula here. We very well know that this is a straight line, and it will obey the equation of straight line y is equal to mx, and we need to find the slope here. So slope is tan theta, you very well know that, and tan theta is the base upon hypotenuse. So this is an equilateral triangle, this is also a, this is a, and this angle is 60 degree. This is actually a by 2, and this angle is 60 degree. So, or you can say that this angle is 60 degree, so the distance from here to here. Uh, you can say that the slope of this line, we need to calculate the slope for this line. So for this line, the slope can be either you would write it y2 minus y1 over x2 minus x1, if you have the coordinates, or if you don't have the coordinates, you just find out tan theta and equate it. So tan theta is perpendicular upon base. So perpendicular here, this is a by 2, this is a, so it is a square minus a square by 4, which can be root 3 a by 2. So this is the perpendicular, and base root 3 a by 2 upon what is the base, it is a by 2. So uh, theta here is 60, yeah, 60 degree, and we very well know that it is 60 degree. And so m, slope is root 3. So the equation we get is, why we have done this, we have done this to find the equation. So equation is uh, root 3 x is equal to y. So this is the equation we get. And why we need this equation? We need this equation just to evaluate these two terms. So so dy, it is given as root 3 dx, and if we put these terms into these terms here, we can easily calculate uh, the the integral. So similarly, we can calculate df3. It will be given by mu naught I square upon 2 pi y. Again y because the limits will be using it for y only. That's why I'm again using. You can use x also, but the limit then you have to choose is you need to vary x from this equation. You need to choose how to vary x. But I am, for simplification, I am using y. So dx I cap plus dy j cap plus dz a cap cross. Here also magnetic field is in this direction. So but the thing is, here in this uh, for the this part, for this part, the direction of dl will be reversed. Why it will be reversed? Because let me clarify it. Because as you choose, dy will be decreasing here. All right. So if dy will be decreasing, so it will be negative here. So if dy will be negative, so what we will be left with, will be left with mu naught I square 2 pi y and dx uh, j cap plus plus dy I cap. But the thing is, we this component, this I component will be cancelled because it will be negative, because dy, it is decreasing now, no? I the I So dl, this term will be negative for y. That's why it will get cancelled with this, and we will be left with the term only. So f net will become the df2 plus df3, but only the terms which contain y only. Now I hope you y only means y component only. So that's why mu naught I square upon 2 pi y, and so I'll be f net we are using now, so I'll be using integration now instead of df. So mu naught I square upon 2 pi, sorry, pardon me, mu naught I square, mu naught I square upon 2 pi, and here dx will be left with, and one d and one y we are. But now we need to define our limits. So limits are simple. We need to go from here to here. We have just concluded that we have just finalized this and this thing, and we need to calculate these 2 points because these are the limits. So first of all, this point is this what is the distance from here to here. We need to calculate it. This is s by root 3, because this distance from here, from the origin, it is s by root 3. I hope you understand why s by root 3, because the y distance was s here, and the slope was root 3. So the x thing which is left with is s by root 3 only. So the x limit, oh sorry, x coordinate is s by root 3. I hope you got that, because s is the distance now, from infinite wire to here, but what we need is the x limit. Why? Because we are doing integration with respect to x. I think I mentioned y previously, in my comments, but we are doing integration with respect to x, so we'll be using the x limits, sorry. So x limits means we need to put the limit of x. I hope you already know that if you are a master student. S by root 3, and this coordinate is s by root 3 plus something. Why plus something? Because it has gone so far na, so this coordinate will be added to this, so s by root 3 plus a by 2. This is the x coordinate, and we also have the y coordinate. If you are planning to make things opposite, putting dy here, then you can easily calculate, uh, easily put the limits of y. So I hope you understood, because the x coordinate, this is the x coordinate, and it is a by 2. So s by root 3 plus a by 2 total limit. So the limit is s by root 3 plus a by 2. So on further simplification, we get mu naught I square 2 pi, and now we need to put the value of y here. So from that equation we got is y is equal to root 3x. So y is equal to root 3x, so it will be 1 root 3 here, s by root 3 plus a by 2 dx by x. So we get mu naught I 2 root 3 pi into ln, will be getting ln s by root 3 plus a by 2 upon s by root 3. So this is the value, and one negative also. We have negative because of these terms, so we'll be getting one negative also. So this from here we get f net due to a straight wire on a equilateral triangle, and for a square loop also. You just need to remember the coordinate system, the formula, and the little calculation should be, you should be good at calculation. So if you are, I recommend you to watch the video and just try it with the putting dy here. How can you do that? You just take this as 2 and this as 3, and then calculate by taking the current opposite, and it will help you to take the dy coordinate, dy small length. So that's all for this video. I hope you understood it, and if you not, let me know in the comment section. I'll solve some more problems on uh, these questions, and will help you solve them better. Thank you. Bye bye. See you. Bye bye.